It's a very great pleasure to have Wendy Freedman here. Wendy grew up in Toronto and did her PhD there. Now I have to read it off on young stellar content of nearby resolved galaxies. And after that, she actually moved to Pasadena to Carnegie Observatories, where she then became a staff member, and then she also became director. And then she just, quickly initiated GMT a little bit. And then she moved to Chicago as a professor. And so she has a lot of recognitions. Very recently, she got the Gruber Cosmology Prize. She got the Danny Hyman Prize for Astrophysics. And she got recently elected as a AAS Legacy Fellow. And also, I didn't know that she has an asteroid named after her. It's a number, if you're interested, it's 107638, also known as Wendy Freedman. And yeah, the stage is yours. Looking forward to meet up. Yeah.
Great, I can take
No,
it.
you have to, I think you have to.
I have to keep it on?
Yeah.
Okay, in Chicago, we're allowed to take it off. Okay. Well, thank you for the invitation to speak. It's really nice to be back in Pasadena. I was remembering this morning, the last time I think I gave a Caltech astronomy talk was the day that WMAP was going to announce its first results on cosmology. And I remember thinking, we had just finished the key project. We had found Cepheids and a couple dozen galaxies. We had calibrated a number of different secondary methods. We finally had a robust estimate of the Hubble constant, an accuracy of 10%. And I thought, what if WMAP finds 42? And that was the value Alan Sandage had published a few years earlier. It's also, you recall, the answer to the question in Hitchhiker's Guide to the Galaxy. But fortunately, WMAP did not find 42. It would have been terrible timing to give a talk if that had happened. But it agreed at that time very well with the measurements we had made with Hubble. We had found a value of 72, and WMAP's first value was 71. And there was cosmic concordance for a very brief period, maybe a decade. It was unusual. Nobody was worried about fighting about the Hubble constant. And then Planck came out with its results in 2013, and their accuracy and precision had improved enormously. Their 2018 result gave a value, an inferred value, assuming a cosmological model, a lambda cold dark matter, what had become the standard cosmological model, gives a value of 67 or so. And yet the values of the Hubble constant based on Cepheids had remained in the low to mid 70s for some time. And the issue, of course, is systematics. And it's an interesting question because it would imply that there is physics in the early universe that we really had no other way of getting a handle on. But we need to, of course, ascertain whether or not there are still systematic errors in the distance scale that have been very hard to overcome. And so at that time, when I was moving to Chicago, Barry Medor and I decided to start essentially a new key project, working from the ground up to measure distances using Hubble and a different technique using red giant branch stars, the luminosity at the tip of the red giant branch. And to do that in galaxies where type Ia supernovae have occurred, and then build up the distance scale from scratch and compare that with the Cepheid distance scale. Because no matter how many galaxies are measured using Cepheids, the issue again is systematics. Root n is not going to help you. And we'd like to understand if there really is new physics that is required in the standard, above and beyond the standard model. So let's see if this works. No, I would say. Okay. Oh, that's interesting. I don't see my cursor to advance. Let me just yeah, the usual. Maybe just click that one. Okay. Now the values of the Hubble constant based on Cepheids are shown here since the time of the key project. So that's the value that we got, 72. And since that time, the values of the Hubble constant based on Cepheids, and largely now using type Ia supernovae, and I'll explain why in a moment, have given values maybe in the mid 70s. And what has changed is that the error bars have come down quite considerably. And does that work? Yes. Whoops. Okay. Now how do I go back? Here are the inferred values from the cosmological background fluctuation measurements. And so this would be approximately the date of my last Caltech talk. And they've come down quite considerably since the WMAP first measurements. And what really has shrunk are the uncertainties. So here's the Planck 2018 result that gives 67.4 with an uncertainty of only 0.5. This is a recent point from ACT combined with the WMAP results, the final WMAP 9 results. And if we take now the errors at face value, then there really is no overlap with the recent Cepheid measurements and CMB measurements. This, I should point out, is an early measurement from the Carnegie Hubble program, which used Spitzer. We measured 3.6 micron Levitt law or period luminosity relation and recalibrated the key project distances. So that gave a value again mid-70s. And the tension between the Cepheid and the CMB measurements now has variously been described as somewhere between 3 to 6 sigma. And that is very different meaning, I would say, in astronomy than it does in physics. 5 sigma really is the standard in physics for something that has been established, and I think without question. But the issue now is how well determined are the error bars, and is this a significant difference? And people will differ on that issue. So just to give you some flavor, what we did in 2019, this was the first publication of the sample that we observed with the Hubble Space Telescope, time into 18 at that time. We have 19 calibrators based on the tip of the red giant branch. I think we were expecting that we were either going to confirm the higher Cepheid result or the CMB results, but we landed right in the middle. And this is a paper that I just published a couple of months ago, which now is based on 4 different anchors. The calibration we've strengthened quite considerably. At the time we published our results, first results in 2019, we had only 1 anchor galaxy, and that was the Large Magellanic Cloud. And I'm showing here, this is a compilation that was put together by John Huckra, who was a member of our key project team. And he looked at the Hubble constant measurements. He actually looked at them historically going back to Hubble and before. But in this case, he was looking at the measurements between 1955 or so and 1990. And he coded the points. So the solid circles here were values published by key project members. And de Vaucouleurs is shown with the stars here, Sidney Vandenberg, and Sandage and Taman were down here. So you can see that that's where the factor of 2 discrepancy, the people are arguing between values of 50 and 100. And eventually we've now converged to the value around 70. And so the range of values that we're now seeing a discrepancy in narrowed quite considerably. But interestingly, if you look again at the publications of values of the Hubble constant over time, since 1980 here, based on all methods, that really hasn't changed in terms of the mean, mode, median. The scatter has come down quite considerably, and so the points around 1980 have larger scatter, but the distribution has narrowed in recent decades. But the median is somewhere just under 70, which is interesting because if you read the literature, you might again have this idea that there's this dichotomy between 2 very distinct values. Now, the measurements of the microwave background fluctuations, of course, people are familiar with, but let me just point out that with the Planck 2018 measurements, if you fit the acoustic oscillation spectrum with 6 parameters in this fit, you don't measure the Hubble constant itself directly, it's inferred. You can determine the current expansion rate given this model, this standard model. And you can see that it's an exquisite fit to the data, measuring now many peaks, not only in temperature, but also in polarization. And it's really an exquisite experiment. So the question still remained, could there be systematics in the Planck data? And I think that's been answered by recent measurements from ACT and also the Lambda Cold Telescope, SPT. But it's again consistent, entirely consistent with Lambda CDM and with the Planck results. completely different experiment done in Chile, different systematics, different detectors, etc. So at least in terms of instrumental uncertainties, I think there's a lot of confidence that the Planck measurements are likely to hold up. But again, the value of the Hubble constant that comes from the microwave background is an inferred value. It's not a direct measurement from the CMB fluctuations. So why is the Hubble tension interesting? And I think it's an interesting question because the current standard CDM model really has been very successful, remarkably so, over a wide range of scales, not just in the CMB fluctuations, but measurements of the matter power spectrum. And if there are missing elements, and one would not be surprised in a model that now is composed of dark energy and dark matter, which contribute most of the matter energy density in the universe, and yet we don't have a physical understanding of what the dark matter is yet, fundamentally what the dark energy is, what the inflaton is. And if we're going to get information, and again, the inferred value of the Hubble constant based on Planck observations is better than 1% precision. And so the way that you would test the model to see if there are cracks in standard Lambda CDM is to measure a Hubble constant to that, not just precision, but also accuracy. And so I think it's really vital that we undertake tests of the standard model, especially given our lack of understanding of the major constituents. So if we say for a moment, we have systematic errors under control, the difference is real, what could explain that potential difference that we're seeing? And many different possibilities have been investigated over the last several years. I think there was a lot of enthusiasm early on for perhaps another relativistic species, say sterile neutrino or some sort of form of dark radiation. But the interesting thing is that the CMB measurements now have gotten so precise, and the measurements of the peaks in the CMB spectrum are so well determined that if you change the Hubble constant, you're going to shift the peaks. And so that the constraints really are very stringent. And many of these avenues that have been investigated can bring the Hubble constant to maybe 70, but cannot bring it to 74 or 76, as some of the recent measurements have been suggesting. The idea that maybe there could be a different equation of state, that is that the ratio of pressure to energy density of dark energy is not -1 or cosmological constant, that it could have some wiggle as a function of redshift. There are now, again, very strong constraints that come from measurements of baryon acoustic oscillations as a function of redshift, and also tying into type Ia supernovae in a relative sense, absolute calibration, but just the form of the evolution. And you'd have to have something very, very contrived at this point, given these other constraints. And many other possibilities, for example, dark matter particle that's decaying. People looked at modified gravity, non-zero spatial curvature, non-Gaussian primordial fluctuations, and a lot of attention recently has been placed on additional physics in the early universe before recombination. And so you aren't affecting the peaks in the way that people were investigating early on. So perhaps you have some scalar field that would decay right before recombination. It wouldn't affect the peaks that we are measuring today. And but it would have to decay right at the point where you couldn't measure the effects. And so I think, again, maybe there is an explanation out there, but so far there really is no good physical explanation that people have been able to find. And that's despite a huge amount of effort. So as of a few months ago, there are over 850 papers written trying to explain the H0 tension, not yet successfully. Now, this is a very simplistic plot, and I sometimes think, why do I have to say this? But we talk about an era of precision cosmology, and I really hope we're beginning to talk about an era of accurate cosmology, because if we continue to miss the bullseye, and we are getting precise distances now, we are measuring those very precisely, but the question is, have we achieved the accuracy to test, which is an extraordinary claim, again, really does require extraordinary evidence. And the name of this game is systematics. This is the tension that people are arguing about, the difference in the Hubble constant, and then just divided by the Thommen quadrature of the uncertainties in each of the techniques. So if the Planck measurements are getting 67.4 with an uncertainty of 0.5, and we want a 4 sigma measurement, then for the Cepheids, if the Hubble constant is 73, we need a statistical plus, the statistical and systematic uncertainties to be less than 1.8%. So have we reached this point where we have both the statistical precision and systematic accuracy at that level? What do we need to convince ourselves of? And I've made, so we would need an uncertainty in the Cepheid measurement of 1.3 kilometers per second per megaparsec. So potential systematic, so this is not an exhaustive list and I'm not going to go through it in detail, but just to give you a flavor of the kinds of things, there's an implicit assumption that the reddening law is universal, seems to hold up. We have no evidence that it isn't, but it's an implicit assumption in the measurements and that it holds from one galaxy to another. The photometric calibration uncertainties have to be small, and I'll mention in particular, when you're measuring, for example, the luminosity of a Cepheid in the back or against the background disk of the galaxy where the Cepheid resides, you have to do a correction to total luminosity, and finding isolated stars where you can make such a correction accurately can prove very difficult, and it often is not included in the overall error budget. If there's a difference between your calibrator galaxies, your anchor galaxies, and your target galaxies, that, given that there are only 3 anchor galaxies at the moment, could be significant, certainly at a 2% level. Metallicity effects, I'm going to describe in more detail. We don't understand yet what the effect of different abundances are, what the effect is on the luminosity of a given Cepheid. And then we have the difficulty that as we move farther out in distance, of course, the resolution of your detector remains the same, but crowding, blending of images becomes an increasing problem with distance. And in the Hubble Space Telescope really is being pushed right now to its limits. We have, as I mentioned, a small number of anchor galaxies, and then there are the unknown unknowns, the Donald Rumsfeld types of errors, what you don't know. The tip of the red giant branch, again, universality of the universality of the reddening law, photometric calibration, which I'll mention is simpler because we can observe TRGB stars in the halos of galaxies away from the disk. We have no choice for the Cepheids. Cepheids are young, they're found in regions near where they were formed. There's dust, there's gas, there's a high surface density of the background of the galaxy. You have no choice. And then, of course, there could be unknown systematics, but the effects of metallicity, as I'll show you in crowding and blending, are much reduced for the TRGB stars, which is why we're so interested in following that up. And then supernovae, again, these don't seem to be large effects on their own, but when we're talking about getting the total uncertainty less than 1 or 2%, then these kinds of things could ultimately contribute to the error bar. So can we definitively rule out cumulative effects that are greater than that level? I would argue at this point, no, but I'm optimistic that in the next few years, I'll show you that we have a way of getting around these, but I don't believe we're there at this point. Now, the Cepheids, as I said, they're beautiful distance indicators. At the 5% level, I'd say at the 95, maybe 99% confidence level, 5%, they are beautiful distance indicators. 1%, I think we still have to demonstrate. Now, here's the result from the key project. So this is just simply velocity versus distance. We're only going out to distances where the other cosmological parameters don't affect significantly the linear expansion of Hubble law as first seen by Hubble. And we used Cepheid, as I said. We actually tested the Cepheid distances based on tip of the red giant branch and RLIs and other techniques that were available at the time. And we calibrated these 5 different secondary methods. The supernovae, as you can see, go out the farthest, and they have the smallest dispersion. So here's the scatter about the Hubble fit. We got a value of 72. And this line here is a velocity of 5,000 kilometers per second. And you can see that some of these other methods, because the distances are relatively close, we can't measure these as far out as we can, the type 1a supernovae. The peculiar motions due to gravitational interactions are a large fraction of the uncertainty. And I point that out again because recently, for example, there have been 6 measurements of distances using water megamasers. The most distant of those is 130 megaparsecs. And One of the galaxies is at 7.5 megaparsecs. So peculiar velocities are a very large fraction of the overall uncertainty. Surface brightness fluctuations have been recent measurements of those. They go up to about 100 megaparsecs. And they're calibrating largely elliptical galaxies with Cepheids that are found only in spiral galaxies. Very steep color dependence, and so that the possibility of additional systematics, I think, is large, but also peculiar velocities are an issue. And then the gravitational wave sirens, the neutron star binaries that were followed up after the LIGO discovery. There's one object, it's at 43 megaparsecs. Again, peculiar velocities are a large fraction of the overall uncertainty. This is the final result that we got, combining the different methods. I should say the supernovae now, we had a small sample at that time, but there are now 1,000 supernovae or more and climbing. So the statistical uncertainties have come down quite considerably. And this was just the relative probability density distribution shown here for the different methods. And the Gaussians here represent the statistical uncertainties, which we designed the project so that the statistical uncertainties would be at a 5% level for each of the methods. And then we could investigate what the overall systematics were if we wanted to get an overall value robust to 10%. And so this is the cumulative distribution, and the bars here are showing the systematic uncertainties. And this result really to that accuracy has held up over time, as we've seen. We don't yet have, so there's been a lot of work on the Cepheids, but not much in terms of other methods of getting those to the same level as the Cepheids, either statistically or in terms of systematics. We used Spitzer to obtain 3.6 micron data for Cepheids in the Large Magellanic Cloud and the Milky Way. And we did that so that we could recalibrate the key project distance measures. And this is the Leavitt law, or the period luminosity relation at 3.6 microns. And here are the Cepheids in the Milky Way. We had independent parallax measurements for them using the Hubble Space Telescope and applying guidance sensor in 2012. And then this is a sample of Cepheids in the Large Magellanic Cloud. The scatter in scale relation for both of the objects amounts only 0.1 magnitudes. That's 5% of the distance, and that's for a single Cepheid. So if you have 100 Cepheids, which we had, then statistical uncertainty is less than 1%. So again, if it was only statistics we had to worry about, we would be done. But it's systematics that are the issue. We measured a distance to the Large Magellanic Cloud based on this parallax calibration. It agreed well with what we had adopted for the key project, so that wasn't much of a change. It gave a distance of 49.6 kiloparsecs. And again, calibrating the key project data led to a value of 74, and that's just the statistical uncertainty shown here. I just mentioned that in the more recent past that Petrinsky et al. Have measured a distance to the Large Magellanic Cloud at the geometric determination at 1.3% level to the Large Magellanic Cloud. So independently calibrating via parallaxes with HST and this geometric distance technique for detached kitchen binaries gives very good agreement. And again, for the Cepheids, the value of the Hubble constant is coming out rather large.
Maybe for the LFC, do they account for relates on the far side and this side?
Yeah. And so we have JHK data and 3.6 micron. The scatter is 0.08 magnitudes, and you look at the residuals from the PR relation, and you can measure the tilt, and we can do that really accurately. Yeah.
So a single distance is not used to LFC.
We have a sample of stars from which we can determine the actual geometrical position of the LFC. These are data now from the SHOES program. So they've used Hubble to extend the numbers of calibrators that these are galaxies that have had type Ia supernovae in them. And they measured the distances to 19 galaxies, finding Cepheids in each of those galaxies. So here is the early Milky Way sample with the small scatter that I showed you. This is their sample of the LMC. has twice the scatter. I'm not sure what contributes to that. But you can see the scatter goes up for a while with distance. This is NGC 4258. This is the maser galaxy with the black hole and the water megamasers. Scatter is almost 4/10 of a magnitude, only at 7.5 megaparsecs. M101 is at 7 megaparsecs. You can see the scatter is large, but then it saturates or appears to saturate. But that's really a function of the fact that there's some 2.7 sigma clipping going on. So it would be larger because the uncertainty is larger, which you expect as you go to larger and larger distances. But it becomes tougher. This one's at 16 megaparsecs and only 4 Cepheids were discovered. It's hard to know exactly where to place the TL relation in a galaxy like that. So they're continuing to push out. They're going to 50 megaparsecs now. The more distant ones in this sample are 30 megaparsecs or so. But it's tough with Hubble. These are hard measurements to make in the disks of galaxies. So what do we need to do for the Cepheid measurements to go to the next level of accuracy? And I think we talk about a Cepheid period luminosity relation, but it's actually a Cepheid period luminosity color metallicity relation. And there is a beta term in the PLC relation. The color term is reflecting the temperature, effective temperature of the Cepheid. And there's this quantity gamma, the coefficient. This is the metallicity as measured in H2 regions in the galaxies that were observed. So this is something that we did early on from the ground before HST. The Cepheids are too faint to measure spectroscopic and hydrogen metallicities in individual Cepheids beyond the LMC. So this was used as a proxy. And the unfortunate thing is that 30 years of investigation, there's been no consensus on what this value of gamma is.
So when let's say that we go to 10,000 kilometers per second, recession velocity, then I would say Earth itself, we have 600 kilometers offset. Okay, I'm saying now the peculiar motions have a set of scale. So if I use 500 kilometers as I don't know. I mean, I'm a bit concerned. There's a fundamental flow of peculiar velocities that either you should modulate, or if not, it's a flow.
Yeah, so that's why we don't do this from Cepheids and TRGB alone. That's why we use the type 1A supernovae where we go up to 30,000 kilometers per second. And most people consider on average the peculiar velocity is something like 300 kilometers per second. But you can look at the delta H as a function of redshift, and now the samples are so large. There's 1% deviation. We're not looking at 8%, the difference between 67 and 50. It could, in a total error bar budget in the end, be a 1% effect, but it's not going to contribute meaningfully to the whole overall difference. But we can't do this from Cepheids alone. That's why we have to use the supernovae. We have a technique, I probably won't have time to talk about it, using a kind of carbon star that we think we'll be able to do this in one jump. So we're working very hard on calibrating that, and we have time on JWST to establish whether or not it's exactly as it looks. But I think we need to measure this metallicity coefficient to higher accuracy, and we need to improve the image resolution. What I should say also is that as we go in the interior parts of galaxies, the amount of dust goes up. The abundance, we measure abundance gradients in galaxies, so the abundance goes up and the surface brightness goes up. So this problem of overlapping images or crowding goes up. So these effects are covariant. And when you see the scatter is already 4/10 of the magnitude as you're observing these more distant galaxies, you can hide a lot of 2% effects in 4/10 of the magnitude scatter. That's 20% in distance. Where I think we're really going to be helped is with JWST, and I have to say that crossing my fingers, the launch is in 6 weeks, and we hope that that will allow us to address many of these issues, as I'll show you later. And this is a busy graph and a busy slide, and the reason is this is a complicated issue, but this is this factor gamma that I've been talking about for the metallicity for the Cepheid. These are 3 papers that have been published in the last few months, 2 of them based on Gaia early data release 3 measurements of parallax. This is a paper that is now finding a large effect in the near infrared, which is contrary to everything that's been modeled for Cepheids, observed for Cepheids for the last 3 decades. There's no way of understanding why the effect would be so large in the infrared. This, again, based on Gaia parallaxes, suggesting that this factor gamma is about 4/10 or so minus 0.4. Earlier studies suggested it might even be 0. Theory sometimes gets an opposite sign. There's no convergence on what this is a very difficult measurement to do accurately. And the 2 of the anchors for the Cepheids right now are the Milky Way and the Large Magellanic Cloud. They have a difference in mean metallicity of half a Bex. So the most commonly used value right now, this is the value that we obtain for the key project galaxies. It's a 1/10 of a magnitude then for this difference in metallicity. That's still 5% in distance. If it's as large as minus 0.4, which is suggested by this recent EDR study, then it's a 10% effect. And that's 2 out of 3 anchors that might have effects that could be at a 10% level. Clearly, we need to resolve this before we can make claims that there's fundamental new physics in the early universe. I'm showing here, these are key project fields, optical data taken in the V band at 550 or so nanometers. And these are images, negative images. So you can see the dust lanes here are white. These are nearby galaxies. They're all less than 15 megaparsecs. And the Cepheids are labeled here. But you can see these are complicated regions. There's crowding, there's dust. And as I said, we have no option. That's where the Cepheids are located. So going out to 50 megaparsecs, you can imagine, is going to be even more challenging. And this is just a comparison again of the Levitt laws as we go out in distance, and the difficulty of either finding Cepheids or the fact that the scatter goes up, especially in the H band. And I'll just mention that when we did the early work in the key project, and the work that Barry Medora and I did before the key project, we were demonstrating the advantages of going to the near infrared to observe Cepheids. Reason is that the dust extinction goes down as we go to longer wavelengths. Metallicity effects are predicted to be less, but unfortunately, what gets worse is the crowding. And so the Cepheids themselves, when we look in the disks of these galaxies, so this is NGC 4258 again, here's an optical image, an I-band image of a 45-day Cepheid in NGC 4258. Here it is in the infrared. So there's a scale here of 3 arc seconds, and here's a scale of 1 arc second. So in the I-band, about 8,000 angstroms, it's isolated. You can do accurate photometry, but you can see how the background starts to come up at H. So the advantage of going to the near infrared for reddening, for dust corrections, and hopefully metallicity are wiped out by this worst problem of crowding. Now, this is a 45-day Cepheid. It's one of the brightest, one of the 2 brightest, I think, in this galaxy. And so here's 4 magnitudes fainter. That's a factor of 40 in brightness. And so it's even worse for the fainter Cepheids. And as I said, this is at 7.5 megaparsecs. It's the second closest galaxy in the sample. And already crowding is an issue. And this is the further complication is that these are evolutionary tracks for Cepheids of different masses shown here. On the left are low metallicity tracks and high metallicity on the right. So we have younger age going up. This is the instability strip defined here, the blue edge and the red edge. But you can see, for example, here's the 5 solar mass evolutionary track that crosses once in this case for low metallicity, but crosses many times. So the same Cepheid is going to cross the instability strip many times. So the effects of metallicity may be a function of star formation, rate in the galaxy, and again, you can see why it's such a difficult thing to pin down this coefficient accurately. Now, why did we go to the red giant branch tip? We can go out in the halo, as I mentioned. There's no crowding in the halo. The dust is minimal. These stars can be found in ellipticals as well as spirals. There are issues about supernovae in spirals and ellipticals that may be different. There's a mass dependence of the galaxy and the peak luminosity of Cepheids. a lot of advantages. The metallicity effect is very, very small, and it's calibratable with the TRGB, directly calibratable. Why are these stars so useful? Why are they standard candles? And they actually are standard candles. The Cepheids, of course, are not. You need a period. Supernovae, you need a decline rate. These have a standard luminosity. They're stars that are about 1.5 solar mass or lower. They've evolved often in sequence. They're climbing the red giant branch. They have degenerate helium cores that are surrounded by a hydrogen burning shell. So the hydrogen burning shell is then dumping helium onto the degenerate core. The mass increases, the temperature increases. And when the temperature reaches about 100 million Kelvin, the core, the stable helium burning can take place. And as the temperature goes up, the star can expand, it's degenerate to release the pressure, and you get a thermonuclear runaway. And this position of the core helium flash, it begins to burn helium. It happens at almost constant core mass because of the degeneracy. And it's simple nuclear physics of the degenerate core that's determining when this core helium ignition takes place. So it's happening at a predictable luminosity. It really is a stable standard candle. And observationally, if we look at, here's now the color magnitude diagram or the HR diagram for a nearby galaxy in the local group. And here's the horizontal branch, the red giant branch. And this is the position at which the core helium flash is happening, that we measure the luminosity function of a particular object, and then essentially look for the first derivative in the luminosity function. We're looking for edge detection, a response of this filter that we use. And of course, we do artificial star experiments where we inject stars with a luminosity function similar to the red giant branch and retrieve literally millions of artificial stars so that we can measure robustly the position of the peak and get a statistical and systematic uncertainty. So this is repeatable, and it's, we clearly won't do it by eye, but we could do it by eye. It's that simple. Now there are stars above the tip. These are asymptotic giant branch stars. They provide a pedestal, a background pedestal that contributes above the tip, but the contrast is still large enough to be able to measure where they are. These are early observations that we made. People say, why didn't we use the TRGB before? We did. We just never applied them to the type 1a supernovae. But these are early tracks. These are Yale isochrones that demonstrated that in the I band, the effect of metallicity on the luminosity of these stars in the I band was really quite negligible. It's not true in the bluer band, and it's not true in the infrared. The luminosity increases, but also it's very insensitive to age. And so we did a comparison of these early measurements with Cepheids and Parallax stars and found that at the 10% level, which is what we were working at then, it did very well. But that's why Barry Medor and I went back to revisit these stars with Hubble and to do even better in the current epoch. So these stars have been studied theoretically for decades now. I'm not going to spend a lot of time, but good agreement on when the helium flash occurs. And as I mentioned, there is a wavelength dependence. These stars get fainter in the optical, brighter in the infrared. And the I band really is the sweet spot, which is where we spent most of our time. But we're working hard now to calibrate in the near infrared because we're moving to JWST. And these stars are brighter in the near infrared, so we can go even farther. They have the nice feature, TRGB stars, that the stars that are more metal rich, so these are metal poor clusters shown here, metal rich clusters shown here. The stars we get redder, you can see these are direct spectroscopic abundances shown here, weak lined metal poor clusters, and you can see the strong lines here for the metal rich clusters. But again, we can calibrate the very small effect of metallicity. We see one, but we also tend to concentrate on the bluer regions, the metal poor stars, which are in all the halos because you have a first generation of stars in the halos. Here are the disk fields. These are the fields where the Cepheids were found in this major galaxy NGC 4258. And these are the kinds of fields that we're observing the tip of the red giant branch in. And we can see any stars here contrasted with the disk. But when you use the advanced camera for surveys, ACS, there are thousands of red giant branch stars that we measure. Here are the AGD stars. And you can see again, this very well measured peak, which is measuring the first derivative of the luminosity function. Here are our fields that we observe with HST. Again, away from the disks of galaxies, we try and go along the minor axis of these galaxies, where the photometry can be measured very accurately. You can see here, these are some of the tip of the red giant branch stars in M66. It's at 11 megaparsecs. So doing photometry on these stars is very straightforward. We don't have to worry about crowding effects. This is a comparison now of published Cepheid distance moduli compared to the tip of the red giant branch. You can see the agreement is very good. We're going up to 30 megaparsecs here. And the red points are those for which there are type Ia supernova hosts in measurements that have been made using both Cepheids and the tip of the red giant branch. So these are more distant. Supernovae are rare. We only find them one every 1.5 years or so. They're close enough to measure with Hubble and TRGB and Cepheid. So here's a blow up of these stars in the red. You can see the scatter is quite low in the comparison here. They're doing very well. But in fact, for the more distant galaxies, unsurprisingly, the scatter is larger. But in fact, it's large enough that the chi-squared is large. It's the published distances to these galaxies are large. The uncertainties are small relative to the observed scatter. One reason maybe, as I'll show you in a moment, this again, the crowding is just another projection showing not only is the scatter increasing as you go to the larger distances, but there's an offset in distance as you go to larger distances. So I just want to stress that these are distances to the same galaxies. So this is not early universe physics here. They can only have one distance. This has got to be systematic. And until we understand the differences here, I think it's premature to claim new physics. This is now the absolute magnitude of the supernovae in these galaxies we've measured. For the TRGB distances, the scatter amounts to just over 1/10 of a magnitude. And that's comparable to what we're measuring in the supernovae, but 1/10. And it's larger for the Cepheids. That may be an indication, some indication that some of these issues are affecting the Cepheid measurements. This now is an independent measure of distances using the tip of the red giant branch. Is another group involving Brent Tully. They get the data out of the Hubble archive. They completely independently reduce it using different software programs to get the photometry, to measure the tip and so on. But the agreement really is quite good. The difference, if you use a common calibrator, so for NGC 4258, is better than 1%. And that kind of test hasn't yet been conducted for the Cepheids. No one has gone into the archive and re-reduced all the Cepheid data. They start from the reduced data. So of course they get the same answer, but that step hasn't been taken for the Cepheids. The supernovae, we have an independent sample. This is the Carnegie Supernova Project that Phillips and I started many years ago now, using the different telescopes at Las Campanas, 1 meter, 2.5 meter, and then when the supernovae get very faint, following them up with the Magellan 6.5 meter. And the purpose of this project was not to find a lot of supernovae, but to really follow individual supernovae in detail. So there are 9 photometric bands here, observing the Cepheids before maximum. We use a program that was developed by Chris Burns. It's a beautiful program for analyzing the data and measuring the light curves. And so not only do we have photometry, but also spectroscopy. These stars have very wide bands. To correct decay corrections for the band shifting, you need to pay real close attention to the supernova evolving as a function of phase. So it really is the most extensive and self-consistent data set for dealing with systematics for type 1a supernovae. And this provides input via SNuPy and Chris Burns's work to the Markov chain Monte Carlo analysis, which then gives rise to a Hubble diagram here. This is the Carnegie Supernova Project sample. The blue points here, there are 99 of them, and the red points here are the tip of the red giant branch distances that calibrate the supernovae. So we only use the distances for the nearby ones. They are affected more by peculiar velocities than the more distant ones. And that gives rise to a value of under 70 with the statistical uncertainty shown here and systematic uncertainty. And this was a slightly updated version of what we published in 2019, looking more carefully at the determination of the TRGB in the Large Magellanic Cloud. And at that time, it was the only anchor that we had, a single anchor of the Large Magellanic Cloud. So we've spent the last couple of years trying to improve the calibration of the tip of the red giant branch, and I'll walk through that quickly because I don't want to go too long. But these are now globular clusters in the Milky Way. We have a sample of 46 clusters. Their proper motions are used to determine the cluster membership. Here are different metallicity bins for the different clusters, and they span the range of the metallicities that we're observing in the nearby galaxy. And the composite color diagram we've put together based on the position of the horizontal branch in these clusters. The tip of the red giant branch doesn't know about the horizontal branch, but we can use them after we've created this composite, measure the tip of this composite color magnitude diagram. And that agrees extremely well with what we have found for the Magellanic Clouds. I'll show you both SMC and LMC. We also undertook another test using this maser galaxy, NGC 4258, and there are 15 fields in the Hubble archive that are in the halo of this galaxy. The other group has measured a tip of the red giant branch in this field. These are two of the fields in which Cepheids were discovered. But for all the reasons that I've detailed, here we go, high surface brightness, dust. You can see an H1 map, the arm goes right through. They're blue supergiants. The stars are fainter, unsurprisingly, and it leads to a different value of the Hubble constant. So I would argue that's not where you want to do the measurement. And so In-Sung Jang's postdoc at Chicago, who's done this work, has done a really nice job. Again, artificial star tests and so on, but very good agreement at the millimagnitude level with what we found for the Large Magellanic Cloud. There's been another paper recently. There's two more fields in close to the disk of NGC 4258. Here's the neutral hydrogen arm I was talking about. Unfortunately, this group put both of the fields together, so we can't tell what the difference is. Again, it's coming out fainter. But the disturbing thing is that the difference is 2.6% in distance, 0.055 magnitude. This is a nearby galaxy. As I said, same distance. Until we understand the difference here, I would argue again, premature to claim new physics in the early universe. Fortunately, we have observations scheduled for next month with Hubble, optical and infrared out in the halo. And I think we can resolve this discrepancy. Here's the new data. There are new dust maps available now for the Large Magellanic Cloud and Small Magellanic Cloud. This is work carried out by Taylor Hoyt, student at Chicago. And we have geometric distances to the Large Magellanic Cloud. And now also for the Small Magellanic Cloud, you can see again the well-measured tip is statistically extremely well-defined. Here's the luminosity function. And this distance indicator is a very precise distance indicator when you can use this away from regions of dust. I'm just going to say a cautionary word about Gaia. There have been papers published saying a 1% distance to the H0 based on Gaia measurements of Cepheids in the Milky Way. And our group was extremely excited when the EDR data came out. I think one way to illustrate where we are now, these are parallaxes for the LMC that have been smooth, but there are these fluctuations, the angular covariance, and some of it, this is up to 50 microarc seconds. And there's a 10 microarc second minimum floor of uncertainty, in addition to the 17 microarc second offset that is recommended by the Gaia team. So the Gaia parallaxes right now depend on the magnitude of the star, the color of the star, the position of the star. And ultimately, we hope they're going to get to the 1% accuracy that I think Gaia is capable of. but they haven't yet. There's this minimum systematic error floor that's been documented by many groups, including many in the Gaia team. At the distance of Omega Centauri, that currently is the cluster that is calibrating the Milky Way determination that we have. It's based on the detached ecliptic binary. That's a 5% uncertainty at the distance of Omega Cent. So despite claims of 1%, it's just not possible right now. And more worrisome, or at least as worrisome for the Cepheids, these are bright sources. And the corrections for the bright sources, these are still saturated stars in the Gaia database, are considerably more uncertain. So we just have to wait. There's no way around that. Putting together the 4 new calibrations of the tip of the red giant branch 0 point, using both frequentist and Bayesian error analysis, yields a very consistent value for the absolute magnitude, and yields a Hubble constant, again, just under 70, but this time now based on 4 calibrators rather than the single LMC that we used earlier. Now, if we compare just the result using the tip of the red giant branch, compare that to Planck, it's a 1.3 sigma tension, and clearly not significant. And as several people have remarked to me, if we started with this key project and measured the tip of the red giant branch, we probably would be asking what are the systematics and the Cepheids, but we did it the other way around. And now I think and clearly there can be systematics in both. We have not yet been able to ascertain where the difference lies. Just another note of caution, these are the values of the Hubble constant based on the 3 calibrators available for Cepheids. So there's a large Magellanic Cloud, 4258, and Milky Way. The TRGB is shown in red, and the Cepheids are shown in blue. These are the previous Cepheid measurements. So the distance to the Large Magellanic Cloud, new photometry was obtained using very short exposures on Hubble, resulted in a Hubble constant change of 3 kilometers per second per megaparsec between 2016 and 2019. The Milky Way, originally scanning parallaxes from Hubble, gave a value of 76, and the new EDR results for EDR3 are giving 73, and that's a 4% decrease. So the anchor galaxies, again, so people have done these very elaborate Markov chain Monte Carlo reanalysis of the SHOES data, and they find covariance in the anchor galaxies. But you don't have to do that analysis to say if you change the distance of the calibrators, your Hubble constant is going to shift everything. And we're still shifting at a level of a few percent. And I'll just mention also NGC 4258. If you use the Cepheids to calibrate, let's say the Large Magellanic Cloud Cepheids to calibrate NGC 4258, then you end up with a discrepant distance compared to the masers. And you could argue, okay, that's due to metallicity difference that you don't yet understand well. But the Milky Way and NGC 4258 have very comparable metallicity, and they differ by 7 sigma from the maser distance. So again, that's an issue. This is a point made also by Georgia Staffy, who points out that this is just different slopes for the period luminosity relation. But if you do a joint analysis, which is what's done, the distances that you get for these 2 galaxies disagree with the geometric direct measurements of the distances to those galaxies. So again, something that needs to be understood. Here's a comparison now of many different methods. Here, now it's working. Okay. Here are the cost measurements. This is the DES year 3 results, including baryonic acoustic oscillations and DDM. Here's the tip of the red giant branch and the Cepheids. And these other methods, these are just the uncertainties that have been published by the authors who have made these measurements. And you can see again that the errors are very large, both statistically and systematically. Nothing yet rivals the pure using the Cepheids. And some of these methods, for example, the type 2 supernovae, the surface brightness fluctuations, the MIRAs, are often calibrated with the Cepheids. So if there is a systematic issue with the Cepheids, they will all slide with them. Now, how are we going to resolve this? And I am quite optimistic at the moment. I think there are a number of things that are coming up in the next couple of years that are going to make a big difference. The Gaia team assures us that they will be able to overcome the systematic uncertainties or floor the parallax offset, and they will provide ultimately 0 points for the tip of the giant branch and Cepheids that are at a level of 1%. We have, as I mentioned, new data coming with Hubble for the NGC 4258 tip of the giant branch that should allow us to resolve the current discrepancy there. And I think where I'm really excited at the moment is the upcoming launch of JWST. It's just 6 weeks away. And we've been awarded time to measure both Cepheids and the tip of the red giant branch in the same galaxies. And we will have 4 times the resolution of the H-band camera currently used with Hubble. So if crowding is an issue, we will see directly. We can do a direct test of metallicity. There's a filter on JWST that's at about 4.4 microns. And there's a CO band head that will allow us to determine directly the effect of metallicity in the Cepheid butterfly. We'll get additional wavelength coverage to help us improve the reddening measurements. Same for TRGB, we have this increased resolution, greater sensitivity. We can actually go to greater and greater distances. As I said, these will be done in the same galaxies, the same instrumentation. And we've been developing another method, this method using carbon stars, which will allow us to have a third independent check if that checks out in accuracy. As I mentioned, it's looking very promising. So I think in summary, I'd say that when I started here 3 decades ago, they were measuring the distance to M33, and for the first time being able to use charge coupled devices resulted in a distance that was a factor of 2 discrepant with what had been measured by Alan Sandage.
Yeah, maybe you can use Zoom.
Somebody got ahead. Yeah, but
I have a question, which is not technical, but maybe for the large center giant branch. People always find flat. Could that be?
there is no in the paper by point, but I think it's really careful analysis to compare different galaxies to see what the structure is. It's small in the R-band, as I mentioned, and most of the stars in the halo of the galaxies you can measure is really negligible. And that's because, again, these are the oldest, bluest metal core population in that halo. The redder stars are fainter, so we don't even measure. But we do measure the bluest stuff. So we've done it both ways. We apply the curvature, or we can apply a color cut, and it's insignificant. And as I said, we're going to red just in day out. So it's how it is. But the nice thing is that it's an empirical measure. We can actually tell it. Rely on TV or measures directly. Hold that. Whoops. I don't know if are there any in the chat here. I don't see any hands raised. I don't see any.
What a question. Okay, yeah, this one.
You got one? Okay.
Sorry, I have a question.
Ranga has a question.
Thanks.
Can you ask it or?
Yeah, I can ask it. Thank you for a very nice talk. I'm as skeptical as you are about this evidence for tension as evidence for new physics.
Sorry, we just got your sound, so maybe if you don't mind, give me a question.
Yeah, thank you for an excellent talk. I'm as skeptical as you about evidence for new physics, given all the systematics that you pointed out. My question was about confusion, right? As you go further and further, you always, these are massive, Cepheids are massive stars, so you expect that they're generally in slightly overdense environments compared to average. And as you go further and further in distance, you tend to contaminate the photometry to a larger degree. How is that accounted for in calibrating any bias in absolute magnitude? Because that has the same impact as what you just showed in the TRGB versus Cepheid comparison, because it reduces the distance modulus, right? And that makes H0 bigger. Is that the right way to think about it?
So you're absolutely correct. This problem gets worse as you go farther out in distance. And so to answer the first part of your question, the way you calibrate that or check for that is to do the same kinds of artificial star tests that I mentioned. In one of the earlier papers, the Schu's team provided corrections to the magnitudes that they had applied. Some of those are as large as 1 magnitude. And the corrections depend upon, so you could have stars that are in your aperture. So when you're trying to get total luminosities and you're trying to measure what is in your sky, you could have contamination there, but you could also, as the resolution is getting worse, have stars that are completely hidden below your Cepheid. So the sign can actually change, and it can be it's very hard to ascertain exactly what is happening, which is, I think, why, again, these JWST observations are going to be really important, because we'll see directly 4 times the resolution. Are there what happened to these stars, and particularly in the nearby galaxies? How far out can you go before this is not a significant problem? And so it's an entirely empirical question, and we'll learn the answer to that very soon.
But it would go in the right direction, right? So confusion, yeah, exactly.
Yep. And as I mentioned, so if you get the photometry of your star wrong because of crowding, then you get the reddening wrong. Then you get the metallicity coefficient wrong. Then what you're applying to all these other galaxies, these are covariant effects, and it could have a huge effect overall, even if the magnitude of an individual effect is not large. They're acting in concert.
Thank you. That's very nice.
Wendy, if I understood correctly, the way you measure is you have a magnitude histogram along the red branch and you run a measurement. I'm not sure how well you model that, but because it's a highly asymmetric distribution and there is error still from the low cut up, but not the other way to put down stars, that will bias the position of the tip too high.
So
whether it's significant or not,
Yeah.
you can model.
2 things. We model the luminosity function of both the asymptotic giant branch and the red giant. Right? So we see what there, we inject stars with a similar magnitude distribution. And we also have done some maximum likelihood measurements where we put in a slope, we know what the slope is, and we can do it that way. And in fact, again, the results that we do as well. We see galaxies with LC where the there's very little contamination relative to the number of giants that we measure, but we can put in excessive numbers of stars and see at what point is systematic offset, and it will be at some point, but it's below what we're actually empirically not connected to the population.
Let me start similar to Shui's question. If we have really excellent knowledge of local light-scale structure, could we actually, are there any prospects for modeling pure velocities?
We do that with Supernovae and so on. And there are many models out there, and they've gotten more sophisticated with time. And yeah, if you're willing again to use a model, and then you have to estimate the density of the model. But yeah, you can do that, and I think we will have to do that if we go to chroma, which we can do. But the advantage will be that we don't have to tie into the one that we trade off.
Okay, one last question.
Yeah, so the talk talking on the local memory account. Do you also think there are any models? Okay, yeah. So do you think there are any models systematics for the Planck account?
Oh, there's systematic for the Planck.
Yes, what do you think it's
Yeah, you know, I think they've had really success in the ACT data, which are getting very consistent results. I think there's still issues about whether or not Lowell and Pyle get the same answer that they, you know, they have needed to understand how long that's happening for a while. But there's this parameter, A length that they measure, which statistically should have a value of 1. They measure it how low the value. The ACT results don't find that. They find when they equal to 1. But I think, you know, they argue that this may be now measured under 40 sigma detection are the ones maybe don't see this as a serious problem. But I think right now the fact that the ACT and the data are doing so well is an obvious issue right now. But the ACT probably the describe with W will SPE will have very soon. So there's more opportunities to test this and I think in terms of the early universe physics, there's some optimism that there will be constraints on the early dark matter models, but it is polarization. So this is not much more fun.
From the standpoint that, you know, quantity has a quality all its own, what do we get from Hubble or indeed from W first? We're just going to have overwhelming numbers of supernovae and maybe Cepheids put together like that.
Yeah, I'd say in terms of supernovae, the samples are so large now, the statistical uncertainties are negligible compared to what we're worried about. I think W first is going to be interesting for a sort of a dynamic branch where we really model the entire data. It's going to be so large, really good statistics, for example, I think HFT has been a remarkable machine for finding schedules, and especially nearby, they rely on having not being an issue. And one of the reasons is it's sensitive and optical, and the amplitude is actually lower relative to the red. So JWC is not that often, it's actually the amplitude is low. So finding exactly that, following them up, that up there. But in terms of numbers again, the systematics are not going to be helpful with many observations where you're not getting any issues. So I think there's a lot of work to be done for the Cepheids. I think at work we have to find the period that would be multiple observations, but potentially you can get multiple data with Cepheids, a large sample of galaxies, and maybe kind of have a Yeah, it's interesting. I don't know if I'm about Peter best, but the carbon stars, this physics started to identify those people that are in decades ago. They were looking at stars in the large magellanic cloud, and they divided the coloration into various regions. And they noticed a very small dispersion in J minus K color for this particular region. And they used it to measure the tilt in the galaxy, which is very interesting because you can't have much of an effect in the middle of the big effect, and you wouldn't be able to measure the tilt accurately. It should be very well accepted They weren't taken with as far as on method in mind. But we measured the luminosity function of this particular star, and it has a very narrow sphere. And we compared it to the giant branch, and the total scatter is an order of magnitude. So even if you attribute all the scatter to the particle stars, it's still remarkably different. So at no cost to our JWST proposal, we will get measurements of the same galaxies that are generations that and further, we were able to look at the metallicity of many different galaxies. So the JWST class of stars is the stars that are the brightest as they're moving in their evolutionary phase. That's how the giant there's a hot spot of burning that occurs. And so the carbon is destroyed. And so the later stars, you don't dredge up enough carbon. Dredge up the carbon stars. It contributes to the redness of these carbon stars. And apparently is needing very narrow surgery. It doesn't be correlated with no involved. So we'll see. But again, it's your perception. And so far, it's smooth. And they're brighter than the red. So you could go up.
Okay. Well, let's thank Wendy again, and thanks for coming.
Maybe it wasn't plugged in.
Yeah, so this one doesn't, so if you plug it in here, it doesn't.
Yeah, the battery was running out.
Yeah.
I just plug it in. Oh, this, I think this doesn't work. Yeah. How about?
That's good, Tommy, because the last time I was at it didn't have.
I saw that.
So I have a naive question. Maybe it's, I don't understand Cepheid physics as well as I should, but what is it that you measure as the luminosity? Is there asymmetry or makes you measure something that is not, the mean luminosity of the object?
So, the Cepheid lake curve has this really rapid rise and then sort of a very slow decline. And so,
But are they all the same, or is there significant variation?
the amplitude, there's no period amplitude relation. It's not understood why.
But you convert each one of the data points to a plot, then you do the averaging.
But if some objects have a, you just take some metric of the asymmetry, so plus minus, that's sine, right? Not sine wave, and something else, and does that something else very significantly from object to object? Or
Well, you can even
as a
go,
function of velocity or whatever that, whatever you're measuring as luminosity is gather or bias and that's asymmetry.
So, number one, we don't have individual metallicity, so we never see a correlation like that, unfortunately. But they do have this characteristic sort of soft. So that the amplitude is there, but they have a very characteristic distribution. And so with Hubble, we're also able to plan the phasing of the observations. It's pretty well spaced in terms of the coverage.
are you worried about measuring an individual star and it might have a
I don't know
fluctuation
what
that you
you
miss?
measure as luminosity. That's what I'm confused about. You have to, very like 24 magnitudes or whatever it is. The amplitude, right? And you're measuring something into luminosity, and I don't know what that is.
Well, yeah, it's a mean.
Right, so for me, you're measuring what. And then some other one is. I don't know what you really look at. But you're picking some sample that's somewhere along the way and some model. You don't know what else.
You don't have to fit a model. If you have enough data points, then you have a fair sample of the function.
Can you hear me?
Right. Is there enough variation?
So what happened? Did Wendy's computer die?
Hello?
Hey, can you hear me?
Yes, yes. Yeah, I think,
So what happened? Did Wendy's computer die?
yeah. I think so. It was plugged in, but apparently it needs to be plugged in on a very specific slot on the adapter. The charger needs to be plugged in on a specific slot, and it was, I think, plugged in the other slot, so it just wasn't charging.
Okay. All right. Well, something we'll learn from. Yeah. Thanks for being there again.
Okay.
I guess so. I'll be back next week, so I'll see you then.
Okay. Yeah.
Okay. I was gonna try to ask Wendy a question, but looks like she's busy, so that's fine.
Yeah. Lynn and Tom are asking her their questions.
Yeah.